Thank you very much. Thank you very much, Mathieu. Thank you very much for the invitation. It's a real pleasure to be here today. And I'll try to give you some insight on what we're doing with what we have been doing and what we're doing and what we will continue to do with the gravity project to observe the galactic center and the supermassive black hole or the supermassive compact object at the center of the Milky Way. Okay, so I've been informed that it has to be a little bit simple, but also with some tricky things, so it's in between. We'll see how it goes. Do not hesitate to ask questions, or if you find it too easy, do not hesitate neither, okay? First of all, while black hole seems to be a modern topic, actually it is not. It's quite old. The first time black holes were invented, well actually black stars, was in the 18th century. And essentially when it became clear that the velocity of light was finite, and with a corpuscular theory of light, some great scientists, Mitchell in the UK and Laplace in France, devised a particular system for which the escape velocity would be higher than the velocity of light. And they called that black stars, because they only knew stars, basically, stars and planets. And they had this intuition of black stars. It is not written on that slide, but what is quite intriguing is that the diameter defined for the black star or for the black hole is still correct for a Schwarzschild black hole. It's the same formula. But of course, the theory of gravitation was not correct at that time, was not complete enough, and so we had to wait for the beginning of the 20th century to get the right theory, first special relativity, and then of course general relativity, to get the right theory for black holes. So this is the starting point of this talk, and of course once you have the theory, you need the object, if possible, to confirm the theory, and this took quite some time before we got them, and even longer before we could observe this type of objects. So the theory of general relativity was very important, of course, and the more important is that it was confirmed with some preliminary tests quite rapidly, first by Eddington, by measuring during an eclipse the shift of the light rays due to the lensing effect of the mass of the sun. This we still use and we still see at the galactic center. He also, well, Einstein himself showed his theory was perfectly well explaining the perihelion advance or the perihelion shift of Mercury in the solar system, and you will see that we'll also use that type of effect in what we do with the galactic center. Before this perihelion shift was explained, some people were looking for another planet closer to the sun that would explain the this strange orbit of Mercury, and of course this planet does not exist. And also some predictions were about gravitational mirage, which are nowadays found in any place of the universe, and it's a pleasure to show this fantastic photograph of one of the first photographs of the JWST, the James Webb Space Telescope, on which you see these gravitational lensing effects due to a cluster at the center of the image here. We talked about the JWST this at lunch just a few moments ago. Okay, so we have the theory. Next, we need the object to observe and to test the theory. And hopefully there are astrophysical mechanisms to produce black holes, at least stellar black holes, and of course also supermassive black holes. And this was put together in a theoretical paper by Oppenheimer and Schneider in 1939. So 24 years after the theory of general relativity. So it came quite quick in the end. And two mechanisms are well known to produce stellar mass black holes. Both are called supernovae, but they are of different types. There's one type for stars of masses higher than 8 solar masses, so called massive stars, although there are stars now we know with much, much higher masses, and which at the end of their life, when they are burnt everything they could burn, collapse because nothing can fight against the gravitation, and that can lead to a black hole. It's not systematic, but that can lead to a black hole. Another way is in binary objects, when a compact object accretes the mass of another object who is an evolved star and whose size has increased incredibly, and that allows to bring mass to the compact object, and in the end, to under some conditions, to build a black hole. So we know that it is possible in theory to find stellar mass black holes in the universe because we have mechanisms. The first one that was discovered was Cygnus X1 in '65, so 60 years ago, almost. And it was found through X-ray detection due to the gas that was accreted on the black hole at extremely high temperature. And it was very fortunate that it was a partner of in a binary and a component of a binary system, because then, since the other component was visible in the optical, it was possible to measure the mass of the central object, which turned out to be on the order of 10 solar masses. So that was the first discovery. But at this stage, we are very far from seeing the black hole. We see effects of the black hole on its environment, but we don't see the black hole. And of course, that's a big challenge. These black holes have become very popular with the advent of gravitational wave detectors. So that's very recent. Now 10 years ago. And these gravitational wave detectors, here you have the Ego Virgo gravitational wave detector. It's a French, Italian initially, and now also Dutch experiment close to Pisa in Italy. And together with the LIGO interferometers in the US, they have been very successful in detecting mergers of black holes and also of other compact objects. So what you detect is this kind of waveform, which is extremely tiny. It's 10 to the minus 21 in relative size. But once you detect that, you know the mass of the components and the mass of the final objects. And so this has been an incredible revolution, because that's the first time you can really study in quite some details those stellar black holes, which was not really possible before that. It's a more direct technique than the indirect technique used at X-rays or other wavelengths. And it has led to some incredible series of detections. So this is not really up to date, because this was for the O3 run. Now the run is O4, and so a new update of this stellar graveyard will be published, I guess, in the coming months. But you see already that there are plenty of these black holes, and there was a big surprise that the mass of the measured black holes was the maximum mass was quite high compared to what was expected. You see that the maximum mass is a little bit smaller than 200 solar masses, which was not really expected. And recently also a 33 solar masses black hole was detected with the using the Gaia mission. So we know now that big stars do exist and do end their lives in black holes of size or mass of a few tens or even maybe a few hundred solar masses. So that's for stellar mass black holes. And there are other categories of black holes. The supermassive black holes, which have been known also or suspected for quite some long time. They are supposed to be the engine of this type of object, which we call radio galaxies or quasars for some of them. and they are supposed to be the engine, so that at the origin of these jets, this fantastic jet you see here in the radio. And so this one is a really big one. We think the mass of the central black hole is 4 billion solar masses. So you see it's a completely different category. And the typical sketch to explain what we see is a black hole at the center, an accretion disk around the black hole, so at a scale which is larger than the black hole, but still small for modern instrumentation, surrounded by gas at very high speed, a few thousand or 10 of thousands of kilometers per second, and a torus of dust and molecules. So that's the classical, let's say the classical setup. And there's another class of black holes which we call the intermediate mass black holes. So in the range of a few thousand or 10 to thousands of solar masses, which are expected because we need to build the big black holes with the smaller ones, and we need an intermediary step, but have not been detected yet. So these supermassive black holes, well, actually we know how to form them, but the scenario is not completely established. There are still areas that need a better understanding. So some of them are probably linked to primordial black holes, which were formed just after Big Bang or during Big Bang. Some of them are linked to the cores of galaxies, and at least we know that galaxies merge, and when a merger happens, of course we don't see that in real time because it takes millions of years, but we see different steps or different stages by looking at different kinds, and we know that when this happens, the black holes at the center merge in the end, and so that's an explanation to get to bigger and more massive black holes at the core of galaxies. And this has never been directly observed. We hope that this will be possible with another type of interferometer, which is, I will skip that, I'll come back to that later, which is LESIA, so that's the equivalent of Virgo, LIGO, but in space. It will fly in 2034 now, so still 10 years away, but it's getting closer and closer. And this interferometer will be sensitive to this supermassive black hole. So we'll see binaries of supermassive black holes. There have already been some hints that this is going to happen with another technique, which is to observe pulsars and do the chronometry of pulsars, very high accurate chronometry of pulsars, and detect these background of black hole mergers. Okay. We think that these massive black holes are very numerous in the universe. We think that the peak of these black holes was also almost 10,000 years ago, which is called the cosmic noon. It's also the time when the universe was producing the largest number of stars. And we now try to see if there are also some earlier black holes, or supermassive black holes, that were produced at the beginning of the universe. You see a few here, detected a few less than a billion years after Big Bang on the right here. And this is important, of course, to understand the theory of how you can get these supermassive black holes at our epoch now, at our age in the universe. And on the bottom right, you have a very recent discovery by also the JWST of a black hole of mass on the order of a few million solar masses at a time which is basically 400 million years after Big Bang. So this field is really making great progress, and there are still many things to discover. Now let's come to the suspected one at the center of our galaxy. I say suspected because we are not fully proved yet that it is a black hole. I mean, we have not proved that there is an horizon, for example. We are very close to that, but yeah, if you want to be really nasty, it's not fully sure yet. Sagittarius A star was discovered in the radio in the 70s by Brown and Balik. And what you see here is an image made with a 3 telescope interferometer in the 70s. With nowadays image quality in the radio, it's a bad image. But it's always like that when a technique appears for the first time and produces new things. But it's a fantastic image because what it shows is that at the galactic center you find a powerful source which is point-like with respect to the angular resolution or with respect to the power spread function of the instrument. And the power spread function of the instrument is this big structure you see here in the middle. And I don't think it was the immediate conclusion that the object was a black hole, but it didn't take long that people converged to the fact that it is probably a black hole. So this is when the whole story started. Just a comment on the size here of the image. If you look in this direction where the size is thinner, the size is on the order of 1/10 of an arc second. Is everybody familiar with arc seconds? That's the unit we classically use in astronomy to measure angles. And here I will translate it in a maybe in a more familiar unit. This 0.10 of an arc second actually is about 1,000, or you see 810 astronomical unit, which is the distance to the sun. So at this scale, you cannot be sure that the object you are seeing is a black hole unless the mass is absolutely huge. And the only information you have is that it is not a resolved object. Maybe it's unresolved at shorter scales, but it's not sure yet. But at least it was very bright in the radio and point-like at this scale. So there were several tens of years of several decades of study of this object. First of all, people started to look at the motion of gas around the galactic center, and all the measurements that were made pointed to the direction that the object was really compact. Of course, the size of this compactness was not as compact as a black hole at that time, but the highest the angular resolution of these observations was, and systematically the object was found to be point-like with respect to this angular resolution. So it was never resolved, pointing toward at least a compact object. Okay, so that's what we have in our within our possibilities. Now, if you want to test the hypothesis of a black hole, and if you want to prove that it exists and use them to do tests of general relativity in the very strong field, well, you have to make an observation. And you have to make an observation at the scale of these black holes. And then you bump into problems. And the main problems, well, the first problem is that usually they are black, so they don't emit light, which is not completely true. They emit light because of their environment and of their action on the environment. And you will see that we see Sgr A star in the near infrared. But the biggest problem is their size. The size of the black hole scales with the mass of the black hole. It's a linear relationship. And if you compute the mass for a black hole of the size of the sun, of the mass of the sun, then the size of the black hole is 6 kilometers. And the problem is that stars, of course, are quite far away. And the closest one you could imagine actually would have a size of, so at 1 parsec, which is the scale where we find the first stars or the closest stars, a few parsec. The angular size of this object of a few kilometers at distance would be smaller than the size of a human sail on the moon. Which means we don't have the instrumentation to make images of this type of such a small object. Another possibility are the supermassive black holes. This is much more favorable because the size of black holes of mass of a few million or a few billion of solar masses is a few million or a few billion of kilometers. But the other problem is that they are at the center of galaxies, and the galaxies are even much further than the closer stars we have in our own galaxy. So that may not solve the problem. Well, actually, we are very lucky because the good solution is that one. And the best candidate is the one at the center of our own galaxy. It's a small supermassive black hole because as you will see, the mass of Sgr star is on the order of 4 million solar masses. But if you do the maths, then you end up with a size of on the order of 50 microarcseconds. And 50 microarcseconds is a few coins on the moon seen from the Earth. That sounded completely crazy 20 years ago. But now it's possible to see that. And I also translated that into a human scale. Not everybody has been on the moon so far. So it's a few hairs seen in Lyon from Paris. So you see it's very, very tiny. But now it's within possibilities, as you know, probably. OK, there's a second black hole, which is favorable for these observations, which is called M87 star. So it's at the center of another galaxy, which is 1,500 times more distant or far away than the core of our own galaxy. But by an incredible chance, the mass of these black holes is also 1,500 times bigger than the mass of the black hole at the center of our own galaxy. So in a way, they are of the same size. OK. So this is why we've been studying the galactic center, where some people have started much earlier than me. I started this business almost 20 years ago now. The galactic center can be observed at different wavelengths. If you want to see the black hole and its environment, the best is to go in the radio or at X-rays, but not in the visible. Or you can go in the near-infrared or in the infrared, where you can find stars. You see stars that shine at the center of the galaxy. And when we want to test objects and measure mass, we love stars, because from stars, using the third Kepler law, if you find binary systems or multiple systems, you can end up with mass estimations. So this is what you see at the galactic center. It's not at the same scale as the background image. And the black hole is here. You see you have a perfect triangle, and the black hole is one of the summit of this triangle, and the stars you see at the other ends are called IRS16, infrared source number 16, because when these objects were detected for the first time, the resolution was not good, and so instead of seeing 5 stars, which are now called the infrared 16 something, there was only one blob. Oh, okay. And so you see that there are many, many stars around the galactic center. The closest one, so the one close to Sgr star, called the S stars, and there are about 50 S stars. And they are quite young stars and quite young and massive stars. So that's a priori enough for our business. Now there's another problem if you go to the infrared or near infrared. That's the turbulence of the atmosphere. That does not help you. We're doing that from the ground, not from space. And so we have to fight turbulence. And because of turbulence, the images are blurred. And so instead of seeing this nice cluster of stars, you see the blob you see at the center here. The size of the square is on the order of 80 times the solar system at the distance of the galactic center. So this is a phenomenon which is now perfectly solved, but which was a problem when the galactic center was discovered, when Sgr star, the galactic center, was discovered. So just quickly to let you know and to explain what is the problem and how you solve it. So if you have no atmosphere, you look at a star. Sorry for my star, it's not really a good astronomy star, but at least everybody understands it is a star. And the star is supposedly a compact or unresolved object or a point-like object. So at the distance of the object, it can be considered as a point source, and the point source emits some wavefronts which are flat at this distance. And so without any turbulence, you have a flat wavefront at the input of at the entrance of the telescope. And you get a perfect PSF, which is here, and which is given by the law of diffraction. Now, if you turn on the atmosphere is a gas with some refractive index, and it's a gas with temperature fluctuations. and the refractive index is linked to temperature, and so you have refractive index fluctuations, and having refractive index fluctuations, you have path rays fluctuations as well. And on time scales, which are on the order of the millisecond, so it goes quite fast, and that has been a problem for a long time to correct for that. Now, if you look at that in detail, each of these turbulence can be modeled by like a prism that will deflect the light, and the typical scale of the prism, which is the coherence length of turbulence, varies with the wavelength, and in the near infrared it's on the order of a few tenths of centimeters. So you have a few of these prisms or equivalent prisms across the pupil of a telescope, and so the pupil at the scale of the pupil of the telescope, they are not coherent, and therefore after shifting the direction of arrival of light rays here at the input of the telescope, you have different orientations for the light rays, and it's a bit like the telescope. Instead of seeing one star, we're seeing as many stars as the number of the prisms across the pupil, and therefore it's one way to explain the phenomenon of speckle, and you get a speckled image. And the problem is that the size of this speckled image is much bigger than the size of the diffraction limit, and so you lose in diffraction limit. This is why the images look blurred, actually. So this is a realistic simulation with a real adaptive optics system. Well, you see it's a simulation because there's in appearance no photon noise. There is photon noise, but the source is so bright that you don't see the photon noise here. And it's very nice to show how it works. And this is the situation where you don't have a correction by the adaptive optics. And so you have each of these speckles as the size of the diffraction limit. And the problems immediately comes when you do a long exposure. And long exposure means more than a few tenths or hundreds of milliseconds, which is easy to achieve, of course. And you don't have enough resolution anymore to separate two stars if these two stars are less than this characteristic scale, which is called the Sgr due to turbulence. But it can be corrected, and this is known now. It has been known since 30 years. The system is quite simple in principle. Of course, it took time to make it reality. The idea is very simple. So because of turbulence, the wavefronts are not flat. And so what you will do is reflect the wavefronts onto a mirror, which size will be calculated so that after reflection, the wavefront will be flat again. And of course, the trick is in the calculation. And the calculation, you make it by sampling the wavefront with a wavefront sensor. And you translate the deformation of the wavefront into commands for the deformable mirror, and this has to work in a loop at a speed which is higher than the speed of evolution of turbulence, so basically 1 kilohertz. And if you do that in the image channel, you have an almost perfectly corrected image, and so you recover the angular resolution at the limit of diffraction. So this is what has allowed to make great progress on the galactic center, because all at a sudden you resolve the stars. No, you don't resolve the stars, sorry. You resolve this cluster of stars around the galactic center, and more importantly, you see them move. And to do that, you need to have big telescope, because you need to have the right angular resolution, or the minimum angular resolution. And this field has been very fortunate that in the 80s, there were ideas to build 8 to 10 meter class telescopes in the optical. And we Europeans are very lucky that we have 4 of them in Chile, which are called the VLT, the Very Large Telescope. And the number 4, you will see, is very important for the next step of these studies. Okay. So what you see here is not a real image, but it's a reconstructed sequence of images based on adaptive optics images taken at the VLT in the 19. I was not involved in this work at that time. I was doing other stuff at that time. And for the first time, they could measure the orbit of a particular star, which is S2, which is the brightest star, the brightest and closest star known to Sagittarius A star. And the period of this star is about 16 years, so it's quite long when you have to measure an orbit, 16 years. But at least you can see the star move on timescales of a few years, and now with gravity of a few days when you are close to pericenter. So this was a very important measurement because, first of all, it gave the position of Sgr star in the optical with a very high accuracy. And more importantly, it gave the mass of the supermassive compact object at the center of the galaxy. So the mass has evolved with time. Well, the estimation of the mass has evolved with time. Initially, it was on the order of 3 million solar masses, and now it stabilizes at about 4 million solar masses, 4 point something, 4.2 or 4.3. And all the stars, of course, have been observed. They are further than S2, so the period is larger. But now, with data accumulated over a few decades, we start to have a good idea of the orbits of these objects. So we have a very precise estimate of the mass, and you will see that this keeps increasing. And just a remark, this is the image I showed you, the image of the discovery of Sgr star, and you see it at the same scale here. And what it shows is that these stars, although they are at quite a distance of Sgr star, the closest distance of S2 is 14 milliarcseconds, and that's the size of the solar system, basically. So it's quite huge compared to the size of the black hole, but still, it's much smaller than the size of this image that you see here. So that's considerable progress. Okay, so this was the stars, but there's also another effect or another observation which is very important for what we're doing now. These are real images, and they are shivering a bit. You see, these are residuals of the correction by adaptive optics. But what is more important is that at the tip of the red arrow here, you see a source that is blinking, and actually that's Sgr star. So the period of the blink here was on the order of 20 minutes. And although the image is shivering, at the angular resolution of an 8-meter telescope, the point is not moving at all. You don't see any motion of this blinking point. And quite rapidly, the idea came that what is seen here is probably, to be honest, there were several models at that time, but that was the best model for us, and it turned out to be the good one, apparently. The blink actually is explained by a blob of plasma which is heated, maybe or probably by magnetic reconnection in the accretion disk very close to the horizon of the black hole or the object. And the blinking is due to relativistic beaming and relativistic lensing. So we are clearly here looking at regions very close to the black hole or to the central object. And of course, you would dream of having this sequence of image of Sgr star, because you see here, you see the primary image, you see the secondary image, you see the photon ring here, all these quantities that are very useful to study the object itself, and also general relativity in a very strong regime. So we don't have that yet, unfortunately, but that's a good plan for the future. So it gave us the idea that it would be fantastic to make an instrument to look at the black hole at this scale in order to sample the potential around Sgr star and to make a general relativity test with this very high accuracy. But then the problem is, of course, you need to make images or to get spatial information at the scale of the black hole, which is a few tenths of microarcseconds. And the angular resolution of an 8-meter telescope in the near infrared is 60 milliarcseconds. So there's a factor 1,000. So this is why we built gravity. So we started that, well, the idea was, came up in 2005, and we got first light in 2015, so 10 years later. It was quite a risky project at that time because we knew that we had to gain a factor of 1,000 in sensitivity compared to what interferometers were doing at that time. And we would also need to gain an accuracy of about 1,000 also in astrometry. And that led to a very to an instrument with very tight specification and very stringent specification, but the topic was worth trying actually. And of course, the interferometer is also useful for other topics. And so there was a risk, but if we had failed, then it was not the end of the world, of course. And some other great result could have been obtained, but not on the galactic center. So the very easy idea is that you need a bigger telescope. You need a bigger telescope by a factor of 1,000, if possible. The factor 1,000 is not possible, so we got a bigger telescope by a factor about 20. And you get a bigger telescope by doing interferometer. So you combine the 8-meter class telescope of the VLT, and this is why we have been very lucky to have 4, to get an equivalent telescope of 140 and 40 meters, giving you an angular resolution of 3 milliarc seconds at 2.2 microns. And an astrometric accuracy, as we will see, on the order of 10 microarc seconds, or a few tens of microarc seconds, which is the size of the black hole. So we built gravity, and gravity is at least a beam combiner. This is the big box you see here. It works in the infrared, so we had to cool it down. It has to be very precise. We want to do very accurate astrometry, so we need to measure the path length from the entrance pupil of the telescope down to the beam combination point to measure optical path lengths with an accuracy of a few nanometers. This is what in the end translates into, combined with a baseline of 140 meters, to an accuracy, to an astrometric accuracy of a few tenths of microarc seconds. We need to stabilize the phase. We need also to stabilize the phase in the pupil with adaptive optic systems. So we built 4 adaptive optic systems, and in the end that made the instrument. I'm not sure everybody is familiar with interferometry, so I'll do one slide on interferometry, only one, almost one. Just to give you the principle, an interferometer, if you use the theory of diffraction, the same theory of diffraction you use for a single telescope applies to multiple telescopes. So you can describe the interferometer saying that it is a telescope, but with a funny pupil. Okay. The other way of describing an interferometer is to do, is with the theory of coherence, of spatial coherence. And that's the theory I'm going to show you here in just a few words. So you have 2 telescopes. Well, you have n telescope. It's easier with 2. So the theory is the same. You have a baseline, which is a distance between the 2 telescopes. And you have a scene or an astronomical object you want to observe. Of course, that's my preferred galactic center. And when you observe it, it's not in the meridian of the interferometer, so there is an angle and there's a projection of the baseline, which creates an external optical path difference, B scala Z here, that you have to compensate with what is called delay lines. So you have moving parts, moving mirrors in the interferometer that are called delay lines, excuse me. And in the end, you get fringes. Okay? So that's the same principle as an interferometer in the radio or in the millimeter, except that in the radio and the millimeter, you don't really have a beam combiner, you don't really have delay lines, and you stop at the telescopes. You measure the signals, you measure the phase and the amplitude, and you correlate that in a correlator. But apart from that, it's the same. So the theory that follows is the same. Instead of getting images, you get instantaneously visibilities, which are complex numbers. The module is derived from the height of the fringe, or is the contrast of the fringe. And the phase is derived from the fringe position with respect to the optical path, the zero optical path difference. So this is for the visibility. and this is for the phase here. And so you measure one complex visibility per baseline at a given observing time. And if you get all the possible visibilities of the object, so for all possible baselines in theory, then you can inverse a relationship between the visibility and the spatial intensity distribution of the source. That's the Zernike-Van Sitter theorem, which tells you that the complex visibility is the normalized Fourier transform of the spatial intensity distribution of the source. So if you have all visibilities possible, then you measure directly this spatial intensity distribution, which is basically the image. Of course, in practice, you have a few points in the UV plane, and you have to make an image out of that. And so it's not directly an inverse Fourier transform. It's a bit more tricky, but that's the principle. This is an example here that's on a late type star with another interferometer. And on the top here, on the top right, you have the image of the source. So it's a star with molecules and dust around it. And the bottom right picture is the point source function, the point spread function, sorry, that you can also derive from the UV samples that you have measured. Okay, so that's the principle of interferometry. It's not like a telescope, it's a bit more complicated, but in the end you can get images if you have enough points or enough samples in the UV plane. So of course this is what we're doing with gravity. We're not only doing that, as you will see, but this is what we are doing in gravity. Gravity is a multi-source instrument, so you have a channel for the adaptive optics, so to flatten the wavefronts in the pupil. And in the galactic center we do that with a source which is called RS7, which is very bright. It is 7 arcseconds away, about 7 arcseconds away from the galactic center, and it has also a magnitude of k equals 7, so at 2.2 microns. And we use reference sources to reference the interferometer. That's the RS16 sources that I've shown you in the first image, and you see the triangle here that I showed you on the picture a few moments ago. When we started with gravity, with the first observations in 2016 on the galactic center, the S2 was so close to Sgr star that we could use S2 to reference Sgr star or Sgr star to reference S2. This has lasted for 1 year basically, but that was very useful at the beginning. Okay. The first thing we did was to observe the gravitational redshift with this star S2. We knew it would happen exactly in May 2018, and so we rushed to be ready for May 2018. And that was the first test of Sgr with the instrument, and also in the potential of a supermassive black hole. So what we did was to take images. You see the images we got. They are not the best image you could dream of with an interferometer, but we honestly don't care at all, because what matters here is the distance between the two blobs. And this distance is measured with high accuracy. This is what mattered for us. And we could get another much nicer image by integrating, but that was not the purpose of this observation. And so you see S2 here at 2 different epochs. All these images were taken at between 2017 and 2018, and to our great surprise, we systematically could see the galactic center. So the other bright source here in the field is the galactic center. So it's always bright. We've never seen a dark source. So there's always gas falling onto the black hole or being heated in the black hole area. And in parallel of gravity, we use a spectrometer to measure the reddening or the redshift of lines also in the near infrared. So that's the data set we had at the time in 2018. So there were points from gravity, that's these squares here, but we also had points from previous instruments, basically adaptive optics. And here you have an inset where you see, I have to say that you have error bars here, but the error bars are really tiny, so this is why you don't see them at this scale. And we had the spectroscopic data with the strong effect here at the pericenter passage. Okay, so these are the same data. And what we were interested in here is to make a general relativity test. And so we modeled the orbit with the data points we had. We also modeled the spectrum by taking into account the Doppler shift. And also this B1 term here, so beta is V over C. So the velocity of the star divided by the speed of light. And this By term here is the sum of the Gr effect, so the Gr redshift, and of the Doppler transverse effect. And we made a model which I think this one had 15 parameters. And one of the parameters was this parameter F, which took 0 as value for a Kepler orbit, and a value of 1 if the orbit is predicted is compliant with general relativity. We did the fit, and we were happy to see that the prediction of general relativity is verified at the sensitivity of the experiment at the time. So that was the first confirmation of this redshift effect in the potential of the black hole. And we had very nice byproducts as well. We got the mass of Sgr with a very nice accuracy, less than 1% or better than 1%, and the distance to Sgr also with a very nice accuracy. So we were very happy because the first test was passed. And we knew that we would be able to measure a second effect, that's the precession of the orbit of S2, which is quite difficult to measure because the precession translates basically to this tiny shift in this red square between the orbit at one epoch and the orbit at the next period. So it's a difference on the order of 800 microarc second between the two orbits. You see here is in this top right figure, the shift we would have seen, the precession shift we would have seen if the star S2 would have a semi-major axis 10 times smaller than the semi-major axis of S2. That's why we're looking for stars which are much closer to the black hole to see much stronger effects, and also on time scale much shorter than 16 years. So we also made the same test as previously with another F parameter, the same principle. F is 1 if Einstein is right. The F parameter, by the way, here there can be several F parameters. One due to Schwarzschild precession if the black hole is not spinning, and one due to the length steering effect if the black hole is spinning. For the moment, we're not sensitive enough to see this second one, but that's the goal for us, to measure the spin of the black hole in the coming years. And so the first estimate we got was that F was on the order of 1.1 plus or minus 0.2. So that was a nice confirmation at 5 sigma. And also another nice feature that when you do these precession measurements, you are sensitive to the mass which is around the black hole, which is distributed around the black hole, because it has an opposite effect to the precession of Schwarzschild. So it has a negative precession effect. And so far we've seen no mass, at least no mass bigger than 4,000 solar masses. So the compact object is really alone at the center of the galaxy at this accuracy. We are still doing this test, and we are, since we are searching for more stars around the galactic center, fainter stars, we're making maps of the galactic center. So you see these maps with one technique here, where you see kind of speckles in the image, another map here with another technique. And we use that to improve the precession measurement, the precession measurement at the galactic center. So we did that with the star S2, but also with S29, S38, and S55, and that also went into the same direction, that the F parameter is converging towards 1, and now with an accuracy of 0.14. Okay, so I will skip that for the moment, except if there are questions, And I will end my talk, because I think I'm quite late, with astrometric measurements at the very center of the galactic center. So the technique we use here is not really imaging, it's not very far away, but we're doing astrometry, and the principle is very simple. If you have a two channel or a two source interferometer, then you measure two interferograms, and the distance in optical path difference between the two interferograms is linked to the angular distance between the two objects projected in the direction of your baseline. So that's this B scalar delta Z here that you measure. And so what you are interested in, of course, is this delta Z. And of course, you need several baselines with several orientations to have a good estimate of this vector delta Z. And the whole trick here is that you need to measure, because you're averaging turbulence, you need to measure the average of this distance between the two interferograms with a very high accuracy, and that's the accuracy of the metrology, if you are limited by the metrology, of a few nanometers. And few nanometers, 5 nanometers, 100-meter baseline gives you an angular accuracy, an astrometric accuracy of 10 microarcseconds, which is the Schwarzschild radius in the case of our galactic center. The big difference with respect to the observation of stars is that you never know when flares will happen. And so you need luck, or you try to avoid bad luck. And actually it took us 2 years before we measured 3 flares. And the first three flares were very interesting. They could be more interesting, and so we are observing more flares, as I will explain in a few moments. But they were quite interesting because they allowed us, if as soon as you have a trajectory around the black hole and at a scale which is comparable to the size of the black hole, well, you can show that the object is really compact, because with the size of the orbit of the stars, you cannot say that the object is as compact as a black hole. There's a factor 1,000. Here you can say that the size you measure for the maximum size you measure for the object is comparable to the black hole. So here is the best, of course, we measured. So we measured this orbit. It goes it goes clockwise, sorry. And we could model that with an orbit which is about, in radius, 4 Schwarzschild radii. And the minimum orbit we were expecting was 3 Schwarzschild radii. 3 Schwarzschild radii is the orbit of what is called the innermost stable circular orbit for a black hole which is not spinning. If the black hole is spinning, then this orbit can be divided by a factor of 2. So there's also possibility to measure the spin by measuring the size of these orbits. I'll get back to that in a few moments. Okay, I will skip that. Maybe useful if we have questions. We also measured polarization loops. That is possible with gravity. So we measure the 2 linear polarization parameters of Stokes, Q and U, and we found a very nice loop. We call that QU loop that you see here. And this has been incredibly useful. First of all, the period we found for the loop is the same as the period of the orbit. And this pointed to the fact that first, to get this factor between the orbit period and the polarization period, that you need a poloidal field. So not toroidal field, but a poloidal field. And the loops are caused by light bending, then this is perfectly well explained. And to get this almost perfect loop centered on the QU origin in the QU plane, then you need to have almost a Phison geometry. So that gave us the geometry of the system, except that we are in the galaxy and we were expecting to see the black hole not from the pole, but from the equator. So we were a bit embarrassed by this conclusion, but all the data were clear. What you see here is a comparison of the different techniques we've been using. So the astrometry, the polarization loop, the contrast also of the flares, and they all pointed in the same direction, that the system is very much inclined on the line of sight and at a distance of less than 4 Schwarzschild radii. So the good news is that we had the maximum size for the object, and clearly this is compatible with the black hole, and there are very few, well, there's no other astronomical object we can think of that could explain what we see. There may be some other exotic objects, but for which we don't have a mechanism to explain their existence at the center of the galaxy. But we had this uncertainty, or this strange result that we see the black hole from the pole. And in the end, we were quite happy. I will come back to that in my conclusion. Because there were some very much expected measurements by the Event Horizon Telescope. So it's another interferometer working at 1.3 millimeter. It's an intercontinental interferometer using all the large millimeter telescope, or most of the large millimeter telescope in the world, so that you can get a baseline which is the size of the Earth. And that could make an image of M87 star and Sgr star. And for M87 star, we knew from the beginning that we would see this object from the pole, because the jet is pointing toward us. And that was the first image you have probably seen a few years ago. And we had to wait for 2022 for the publication of the image of Sgr star. And this image of Sgr star completely confirmed what we have detected with gravity. They also see the object from the pole with the same order of uncertainty of 20 to 30 degrees, and with a size which is comparable to what we have measured with the flares. So we were relieved that we didn't get wrong conclusions from our measurements. Let me come back to this graph, and then I will stop. This graph here, we made it when we made this publication in 2018 with the first 3 flares we have observed. And that's a comparison with what you expect. So that's the relationship between the period and the radius of the orbit of the flares. And that's a comparison with the 3 situation. A Schwarzschild black hole, that's the red line here, or the red curve here. A maximum spinning black hole, that's the green light here, and a retrograde spinning black hole, that's this blue line here. And clearly, we are fully compatible with the Schwarzschild black hole, but we are also compatible with any spinning black hole. So that was, for me, a disappointment. And we would need flares with a period of less than 30 minutes to make a difference between a spinning and a non-spinning black hole, and to see if the points would be compatible with any of these two. So far we've been lucky, but not enough to get to that conclusion. We know it's possible because the 2003 flares had a period of about 20 minutes. So we expect one day, when we observe, to see a 20-minute flare, and then we'll be able to conclude if the black hole is spinning or not, and then we'll need to measure the spin more accurately. Okay, I'll stop here. Thank you very much, and if you have questions, I'll be ready.